Now that we've learned torque, it's time to learn about equilibrium when torque is involved. So this section that we're going to be looking at is called Equilibrium and Statistics. And here's basically the definition. In order for an object to be at equilibrium, so what that means is the object is not moving and it's not rotating. So picture like balancing on a seesaw. Two conditions have to be true. Two conditions must be met. One is that the net force must be 0. And two is the net torque must be 0. So in equation form, that looks like this. Net force has to equal 0, and net torque has to equal 0. Now, here's some problem-solving tips for you to use when working with torque equilibrium. The first thing you want to do is draw a torque diagram. And a torque diagram is a force diagram with a few added features. So this is a force diagram including distance from the pivot, from force to pivot. Remember that the weight of an object acts at its center of mass, okay? The weight of the object in other words, it's Fg, acts at its center of mass. So if you have a uniform object, the center of mass would be the center of the object. And the third thing you're going to do is write out the equations. The equations, and you will then solve. Okay, so we're going to try one problem here right now, and then we'll practice more when you get to class. So let me move this board over. This problem says a uniform 40 Newton board supports two children, one weighing 510 newtons. Notice that is already the Fg. You don't have to multiply it by 9.8 anymore. And the other weighing 350 newtons. The support is under the center of mass of the board. Notice the board is uniform, so we know what that means. And the 510 Newton child is 1.5 meters from the center. Where should the 350 Newton child sit to balance the system? So again, the first thing I'm going to do is I'm going to draw a force diagram. So here's my board. Okay? And it says my board pivots at its center. So I'm going to draw a little pivot at its center. And I have two children. One sits here and one sits here somewhere. I don't know where. I do know that this 510 Newton child, this is the 510 Newton child, so what I can do is draw the force for this child. Fg is 510 newtons, okay? I know that this child has also an Fg, and I know that Fg is 350 newtons. I have been told that this child, the 510 Newton child, is 1.5 meters from the center. So this distance is 1.5 meters. And the question is, what is the distance from the pivot to the second child? What is that distance? X meters. Okay, that's what I'm trying to find. So notice this is a torque diagram because it has both the forces and the distances. Okay? Now, if I'm drawing the force diagram, there's one more force. This board has a force, and remember that force acts at its center of mass. And the force is 40 newtons, okay? So this is Fg, so we'll call this Fg person 1, Fg person 2, and we're gonna call this Fg of the board, right? And it's 40 newtons. Now, if I'm going to find this distance, I'm going to set the torques equal to each other. That's what we said in the previous board, okay? If you're looking at this and trying to figure out how many torques are there, well, you can only have a torque if you have distance, right? Because the torque equation is Fd sine theta. If this is 0, then your torque is 0. So you can't have a torque if you don't have distance. If you notice, the Fg of the board is exerted right at the pivot. So there is no distance to the pivot. No distance to the pivot. So that means that the actual Fg of the board does not exert a torque. No torque, okay? So if your force is at the pivot, it doesn't exert a torque because it doesn't have a distance. All right, so we have two torques. And remember that if the torque is rotating counterclockwise, it's going to be positive, and if the torque is rotating clockwise, it's going to be negative. But we're going to go back to this net torque idea and say, okay, if this board is not moving, then the torque that's exerted by this child has to equal the torque that's exerted by this child. Okay? So meaning, I can say torque 1, which is this torque, has to equal torque 2. If that thing is not going to move, they have to exert the same torque. So once I have that, I can plug in some values. I can say F1 D1 sine theta 1 equals F2 D2 sine theta 2. Okay. I know the force for the first child is 510. The distance is 1.5. Sine of 90 because they're perpendicular to the distance. The force and the distance are perpendicular. That equals the second force 350 times the distance I don't know times sine of 90. Okay? So once you plug these numbers in and solve for D2, you will see that D2 is equal to 2.18 meters. What does that mean? That means the second child has to sit 2.18 meters from the fulcrum, from this pivot, in order for this board to be balanced. Okay? And it should make sense to you that because the second child doesn't weigh as much, their distance has to be farther to exert the same torque as this person who weighs more. So their distance will have to be smaller to exert the same torque. Okay? All right, we'll pick up on this when you get back to class and we'll do some more practice.